Okay. Today we'll begin chapter 2, resistive circuit analysis. The first few topics are basically the topics that you've already covered in your prereqs, but I will cover them nonetheless. Okay. So first up is basically resistors in series and parallel. Okay. By the way, we're supposed to be about 30 or 40% eclipse, but I don't see anything. Nothing. Let's see. Share the notebook. There we go. And section 4. All right, so as I was saying, first up is resistors connected in series. So speaking of series, how can we identify two components connected in series? Well, by looking at the nodes. Node is an electrical junction where two or more components come together. And if there are no more than two connections at that node, then those components are said to be in series. So a series connection can have no more than two connections at a single node. No more than two connections. So you could have a resistor connected with another resistor. A resistor could be connected to a capacitor, to an inductor, doesn't really matter what component it is. But if they are connected at one single junction with no more than two connections, meaning there is no other component connected at that junction, then those components are said to be in series. When it comes to resistors in series, there is a small derivation from Ohm's law. But again, that's not something we're going to do. The total equivalent resistance is simply the sum of the three resistances. So as seen in this figure, we have three resistors connected in series. If I label these nodes A, B, C, D, I can see at node B, R1 and R2 are connected and no more than two connections. So I can state R1 and R2 are in series. Similarly, at node C, I have two connections, R2 and R3, no more than two. So I can state that R2 and R3 are in series. And because R1 and R2 and R2 and R3 are in series, we can combine all three of them together and state that all three of them are in series at the outer terminals. These outer terminals are here. And I note that the total equivalent resistance is REQ. So EQ stands for equivalent. So total equivalent resistance as measured between those open terminals. So a real life practical example would be you taking a ohm meter or a multimeter and connecting the two terminals across that meter. You're trying to measure the total equivalent resistance at those outer two terminals. And because the individual resistors are in series with each other, without any break in connection, I can state that all of them are in series. So series connections can have infinite components. Okay, infinite components. And between those outer terminals, I can state that all components are in series, as long as there is no break in the middle. Easy enough? Familiar? The current I, logically speaking, of course, has no other pathway except to flow through R1 and then R2 and R3, which means the current is the same for all components in a series connection. Now, when we say current is the same, it doesn't mean that if the connection changes, the current won't change. Okay. What it means is that the current for R1 is the same as the current for R2 is the same for R3. You could have an infinite connection of resistors or components, doesn't matter what component it is, but the current through that entire series connection will always be the same for all components. In this case, the current I is a result of R1, R2, and R3 all working together. It's the combined cumulative effect of R1, R2, and R3 that gives us that value of I. If we add one more resistor to this connection, or if we take out or remove one resistor from this connection, then I will change. It will change in value, but that value will still be the same for all three resistors or all resistors in that circuit. Does everyone get this? Everyone understand? So current remains the same means that the value of the current is a result of all the components working together. So all components will have the same current. If you change any of the resistors in that circuit, then the value will change. Okay, so it's a difference. When we say it's the same, the value doesn't remain constant. Speaking of remaining the same, if we have a parallel connection, then voltage remains the same. Voltage remains the same for all components. Again, remains the same or is the same, meaning you have multiple connections in parallel, then the resulting voltage is due to the combined effect of all the resistors or all the components in that parallel connection. Okay. How do we identify components in parallel? I always like to say we deal with two terminal elements in this class: resistors, capacitors, and inductors. They all have two terminals each, two ends. So these components are like holding hands. Okay. You have two terminals, and if all the respective terminals are connected together, then we say that they are connected in parallel. Respective terminals of other components or other elements. As with series, you can have infinite number of elements all connected in parallel. So series connection can have many nodes, as many nodes as there are components. And then you have two outer terminals. In a parallel connection, there are only two nodes. Doesn't matter how many components you have connected in parallel, it's always those same two nodes. So it doesn't matter where you actually measure the resistance. Here, we are stating that we measure Req on the left side of the circuit, but electrically speaking, these two are exactly the same. Okay, so you could measure Req here across R1, or you could measure it across R2, or measure it across R3. all 3 points will give you, all 3 measurement terminals are exactly the same because the exact same 2 nodes. So you can measure Req across any resistance, it will still be the same. It's the exact same 2 nodes. There's no difference whatsoever. Does everybody understand that? Right? And because it's the exact same node, if you measure the voltage across those 2 nodes, the difference in potential between the 2 nodes will remain the same. So voltage for every component is always the same. And Req for this circuit is given by the reciprocals of the sum of all the reciprocals in the circuit. So Req is 1 over R1 plus 1 over R2 plus 1 over R3. Yes. That is very good. Yeah. So the question being asked is, if we wish to measure the individual resistances in the connection, would we have to disconnect? The answer is yes. We would have to disconnect. And taking it one step further, this goes into the next slide. So actually 2 more slides. If we have a source connected to a circuit, you have to disconnect the source before you measure your resistance. This is the actual practical equivalent. Whether you are taking the lab or you are not taking the lab is irrelevant. As a professional engineer, later on in life, maybe a few years later, you might be working with circuits. This is something to keep in mind. If you have a source connected to a circuit and you try to measure the resistance, you will obtain an incorrect value. So you do not want to have a source connected to your circuit while you're measuring resistance. You have to disconnect it from the source, then take your measurements. And again, of course, if you wish to measure individual resistance, then you have to you have to disconnect that resistance from that large network and then measure it. Because when we measure Req, the terminals matter. Okay, the terminals of measurement will matter. And we'll take a look at a few examples in the next slide, in just a minute. 2 more tips I'd like to say. We talked about voltage remaining the same. If you have 2 resistors in parallel, the Req is simply the product of the 2 divided by the sum of the 2. So for 2 resistors in parallel, Req is simply the product of the 2 divided by the sum of the 2. And you can do that. 1 over R1 plus 1 over R2 gives you R1 plus R2 divided by R1 times R2. Reciprocal of that would give you R1, R2 divided by R1 plus R2. Okay, that's just a little bit of a shortcut. Sometimes it's very useful. Actually, we will see this. I will show you the usage in one of the example problems today. And then if you have n number of resistors, all with the same value, ohms, then Req is simply R over N. If you have n number of resistors all connected in parallel and they all have the exact same value, the Req is simply R over N. 10 ohms plus 10 ohms in parallel is 10 by 2, 5 ohms. 1 over 10 plus 1 over 10, 0.1 plus 0.1, 0.2, 1 over 0.2 is 5. 100 resistors connected in parallel, if they have the exact same value, it would be the value divided by 100. And you can try it out again. But those 2 concepts were useful. Not concepts, but tips, suggestions. Okay, let's take a look at an example. At this point, I will tell you to all take out your calculators and work this with me. Not work this with me, actually. You work this and you tell me what the answer is. If you don't have a calculator, use a smartphone with your calculator app. We are asked to find the equivalent resistance between the open terminals. In this case, the terminals are given to us at the far end or the far left of the circuit. I'm going to note Req at those open terminals. When you have a circuit like this, you start at the farthest end and you start moving towards the front end of the circuit, meaning I start at R4 and I move towards my terminals of measurement Req. So for A, if I wish to find Req, I would start at the farthest end. I have R4. Then the next resistor up is R3. What can I say of the relationship between R4 and R3? I look at the two terminals of R4 and I see that that terminal goes to one end of R3. I look at the other end of R4 and I see it's connected to the other terminal of R3. So are they holding hands or not? Yes. So they are in parallel. That's my symbol for parallel, by the way. 2 forward slashes, R4 parallel R3, can extend the same concept to R2. And so I can state that all three of them are in parallel. In this case, it's a simple circuit. Our brains can automatically look at that circuit and automatically deduce or conclude that these three are in parallel. Okay, that they are in parallel. And then, if all of them are in parallel, I can electrically or mathematically draw this out. Not electrically. Mathematically, I can represent as one single resistor. So Req is still here. This is R1. I will label this as R5. You can call it whatever you want. RABC, XYZ, Batman, Superman, Iron Man, doesn't really matter. It's a notation. As long as you specify what the notation is, which I will do here, then it's absolutely fine. You're showing me the work. So it's R4 in parallel with R3 in parallel with R2. I simply chose to keep that naming convention. R5 is R4 parallel R3 parallel R2. Again, we are not physically combining them, but the electrical effect is represented mathematically here. Make sense? So R5 is the electrical equivalent or the mathematical equivalent of the three resistors in parallel. So now, if we draw this out like this, we can see R3 and R5 are connected together. They are connected at one single node, and there are no more than two connections at that node. So I can state R1 and R5 are in series, which gives me my Req. Does that make sense? If we simply look at this circuit diagram, then there are four connections. If you simply look at that diagram, I would not be able to state that R1 is in series with R2, R3, or R4. And that would be correct. It is not in series with R2 or R3 or R4. But it is in series with the combined effect of R2, R3, and R4. It's an important difference. All right, any questions? So what is the answer? Req is 1 over 2 plus 1 over 3 plus 1 over 6. What do you have? Anyone? 3? How about just the parallel connection? That is absolutely correct. If it's a series connection, 10 plus 10 plus 10, what is my Req? what is 30 in relationship with 10? It's 3 times, but that's absolutely correct. Larger. I didn't give the option, of course, larger or smaller, but it's larger. Our brains don't think about it. We automatically know, because if we add something, then that value always has to be larger. But what do you see here? 6, 3, and 2, and the resulting REQ in parallel is 1 ohm. In a parallel combination, the resulting REQ will always, always, always be smaller than the smallest resistor in that parallel connection. And this is something your brains have to be trained to look for. It's an important concept to keep in mind. So these kind of concepts, you have to think about those, and it'll be, I don't want to say memorize, but understand and memorize, I guess, is the same thing in this case. Because if I'm solving this, and if I get 2.1 or 2.5, I should automatically think that that is incorrect. Does everybody get what I'm trying to say? Right? So in a parallel combination, the resulting REQ will always be smaller than the smallest resistor in that parallel network. And that's something to keep in mind. Okay, any other questions? Let's look at example B before we move on. REQ is at the outer terminals. I start at the farthest end and I move towards the front end. I look at R4. R4 is already connected here. It's connected to R2. It is also connected to R3. So if I look at the other end of R4, the other end of R4 goes to R1, and it's going to R3. So R4 and R3 are in parallel. So for B, I start at the farthest end. I get R4 and R3 are in parallel. And so my circuit now looks like this. By the way, when you're showing me your work in the quiz or in the final exam, you can draw out the circuit diagram or you can write out the equations. I'm doing both right here. As an engineer yourself, it will always help you to draw it out, especially in this class. R1, R2, and I'll call this R5. R5 is R4 in parallel with R3. Then I can see R2 and R5 are in series. They are connected at one single node. And then I can say this is R6. R6 is R2 plus R5. And then my resulting REQ is finally R1 parallel with R6. Let me know if you have any questions. Easy enough? Okay. Now there's another technique I'd like to show. And as far as I've seen, I have not come across that technique anywhere else. You draw out the two measurement terminals. Okay. Let me use example B, and I'm going to label the measurement terminals as 1 and 2. Now the goal is to measure REQ between 1 and 2. So I'm going to draw out the terminals as horizontal lines. And the goal is to draw out every resistor vertically connected between 1 and going towards 2. Okay. So if I start at the top, I have R1 and R2 connected at terminal 1. Right? Everybody sees that? And I'm going to draw both of them vertically. Okay. So that's R1. And then some distance away, I will draw R2. When I begin solving a circuit like this, we would not have any idea how much space I need, so I'll just make it as large as possible. Then I would follow R1. Again, the goal is to reach terminal 2. If I follow R1, I can see it's connected directly to terminal 2. So I will drop this connection directly to terminal 2. So far, so good. Then R2 is connected to R3 and to R4. So I'm going to split. If there were 3 connections over there, 3 resistors, I would draw 3 resistors. I only have 2, I'm going to draw 2. R3 and then R4. Again, I make my way back to terminal 2 and I can see R3 is directly connected to terminal 2. So I'm going to drop R3 directly to terminal 2. Same thing with R4. And now I can begin solving my circuit. Everything is either in parallel or in series. I can see R3 and R4 are in parallel, which is then in series with R2. And this entire branch on the right is in parallel with R1. Take 10 seconds, think over it. Let me know if you have any questions. Does that make sense? This technique will work on most circuits. I don't think I've seen a circuit where it wouldn't work. There are some circuits which are neither in series nor in parallel, and you try to solve it, and somehow they are, well, not somehow, but the way the connections are made, they're unsolvable. You'd have to go through, roundabout way and applying Ohm's law to determine what the resistance is. But this technique will work for most circuits, especially in the homework problem. There are some circuits which are drawn in the shape of a diamond, and this technique will be useful for those kind of circuits. Okay, about 7-8 minutes left. Let's go into series parallel equivalent analysis. Okay, so we take our technique. So chapter 2 is based off, you learn about resistors in series and parallel, you learn about an analysis technique. Then we take techniques from the previous chapter, we combine all of those together, and we learn about a larger analysis technique. Okay, so this is now still prereq material. But again, if you don't know how to do this, then it's going to get tougher as we go along. That is the reason why the homeworks are assigned. This is the reason why I do this in class. So series parallel equivalent analysis, we are going to use the techniques we learned previously, meaning combining resistors in series and parallel, reduce it down to like one single resistance as seen by the source, meaning we have to remove the source. Remember the point I just made a few minutes ago? We remove the source from the circuit and we measure Req between those open terminals. So my circuit would look like this. Req measured at the terminals where the source was connected. This is R1, this is R2, this is R3. We start at the farthest end. What do I get? R2 and R3 are in parallel. I will call that R4. 2 resistors in parallel. The product of the 2 divided by the sum of the 2. You don't need a calculator for this. How much is this? Anyone? Absolutely. 1800 divided by 90, excuse me, 20 ohms. In Req between the 2 terminals, I can see is now in series, and so it's 10 plus 20, gives me 30 ohms. Excuse me. Okay, 30 ohms. Now I plug the voltage source back in. And this is Req, and this is Vs. So remember chapter 1, we said when we begin circuit analysis, we have no idea of the voltage polarities and current directions. We make our assumptions, arbitrarily assign current directions and voltage polarity. But those assumptions are based on certain rules. They're based on certain logic. The first rule, which direction is the current for the source? Negative to positive. Current always goes from high to low for all components, all passive components, except for a source, right? So for a source, it always goes minus to plus. Minus is at the bottom, plus is at the top, current's going up. It's a circuit diagram. When you have something on a physical bench, it could be any. So if it's going up, it has nowhere else to go except enter R1 to the right. Current goes from high to low, plus to minus, meaning point of entry in a resistor is goes from high to low. Point of entry is plus, point of exit is minus. That is my assumed polarity of the voltage for R1. Then current hits this junction, splits in two. I call it I2 and I3. And again, current is entering from the top. Point of entry is plus, point of exit is minus. And because they are in parallel, the voltage polarity applies to R3 and it applies to R2. Applies to both. They are the same node, right? If they are the same node, that voltage polarity applies to both. So now that I have my Req, I can calculate Is, and Is is simply Vs over Req from Ohm's law. So 90 divided by 30 gives me 3 amps. So I took my large circuit, I compressed it down to one single resistance, I calculated my current. Now I expand it back up again step by step in the reverse order. So if Is is flowing through Req, it is also flowing through R1 and R4. So I can find, this would be V R4, and VR4 would be Is times R4, which is 3 times 20, which gives me 60 volts. VR1 is equal to Is times R1 is 3 times 10, 30 volts. KVL, voltage source is 90. Supplying the energy has to be absorbed by the resistors. 90 minus 30 minus 60 equals 0. Answer is correct. If VR4 is 60, I can find I2 as VR4 divided by R2, which is 60 divided by 30, 2 amps. Oh, out of time. If you have to leave, you can leave. 60 divided by 60, 1 amp. 3 amps total current coming from the source. 2 plus 1, 3. KCL is also satisfied. One final point. Voltage across a resistor is always directly proportional to the value of the resistance. The higher the value of the resistor, the larger the voltage across the resistor. Current is inversely proportional, meaning the larger the resistance, the smaller the current, and the smaller the resistance, the larger the current. And you can see that reflected here. 30 ohm resistor has a larger current, 60 ohm resistor has a smaller current. All right, homework is due tonight and homework is due on Wednesday. If you have any questions, reach out to me. Student hours this afternoon. Send me an email, meet on Zoom. Be happy to answer any questions you have. Good day, and I will see you all on Wednesday. Just